Hello, and this is my video presentation on the Urysohn metrization theorem. The way I chose to do this is that I will break it up into a few parts. This is going to be part one, and in part one, I'm going to state the theorem, and I'm going to give a quick sketch of the proof. And then in part two, I'm going to get into a little bit more details of the proof, which were left out. So the Urysohn metrization theorem is a theorem about topological spaces, and it gives conditions that a topological space can fulfill, and if the topological space fulfills these conditions, then it's a metrizable space, which means a metric can be put on it. So this theorem states that every regular space X with a countable basis is metrizable. To get an understanding of what a regular space is, we can look at figure A. And figure A shows a topological space, and there's a point, and there's also a closed set of the disjoint closed set of the space, and those are shown in black. And you can see that they can be separated by two closed sets, two disjoint, open sets. So that's what a normal space is. It means you can separate a point from a disjoint closed set. Now the second condition is that it has a countable basis. The space X has a countable number of basis elements. So in the most general terms, what our theorem is going to involve is that we are going to embed X into a metrizable space Y. Now an embedding is a homeomorphism from X into from X to a subset of the space Y. And what we know about homeomorphisms is that they preserve topological properties. So if we can embed X into a metrizable space Y, we know that it will be metrizable. Okay, so now let's get into the proof. So the first part, well, before we even start the proof, we first have to choose a metrizable space Y in which to embed X. So our choice of Y is going to be R omega in the product topology. And this was proved in chapter 20 to be metrizable, so it's a valid candidate for our proof. So now step one of the proof is a bit of a mouthful, but it's going to be very important in this embedding. So what we have to do first is we have to show that there exists a countable collection of continuous functions, fn of x, from x to 0, 1, the closed interval 0, 1 of R, such that given any point x naught of x in any neighborhood U of x naught, there's an index n such that fn of x naught is positive and fn of x is 0 for x not in U, meaning it's 0 for any x outside of the open interval of x naught. Okay, so this is step one of our proof. And this is, in my opinion, the main part of the proof, because this is the part of the proof which relies on the properties of regularity of x and also on the property of the countable basis of x. And this is really the most difficult part of the proof. And in part two of the video, I'm going to go into more detail exactly on how the proof of this first step goes. Now, step two is a little bit more simple. Step two is that given our collection fn of x, this countable collection of countable functions with the special properties that we just went over, We now define another function. We define a function capital F of x from x to r omega into r omega by the rule that f of x is equal to f1 of x, comma f2 of x, and so on and so forth. And this is going to be an element of r omega. So this function is actually going to be proved to be a homeomorphism. And this is going to be a homeomorphism between x and a subset of r omega, which is, of course, an embedding. So that is really what we're trying to prove, that there's an embedding of x into r omega. So this is the end of part 1 of the video. In part 2, I'm going to go into more detail of the 2 steps and how we prove them.